So yeah, if you are doing a lecture, it's all described in here, but I want to make sure this is very clear. Your PR, if you're doing a lecture, your pull request must be merged at least one day before your lecture. If you submit it the day, it's not good. The day before, I'm not merging it. There's no way I'm going to accept it. I will not accept anything on my website that is garbage. Last year, I don't think a single student got it right on their first try. And it takes a lot of back and forth because you can't follow, they never followed instructions. So, follow the instructions. There's instructions. You have to make it such that, because if you do something wrong, you'll break my whole website. So I can't accept it. You must check it. When you do that, if we go to the GitHub page, if we go to like any of the closed pull requests, let's see. Like, okay, there's two things I want to show you here. First, let's go back here. If you go down to the README, you've set up your virtual environment, and if you set up your virtual environment correctly, you will be able to run the following scripts, or commands, really. You just type format, and it'll make sure all the code is formatted correctly. If it's not formatted correctly, when you submit the pull request, it'll fail. Because your code has to be correct before, like it'll automatically tell me that it's failed. I don't mean you failed the lecture, no. I mean like the pull request on GitHub fails. You also run your unit tests. You should also build locally. Now, for those of you that don't know, it blew my mind last year how no one knew what this is. This is a stand-in. So if you have bash, this could be like a path variable, but this is a stand-in for whatever the source directory of the thing you want to build is, and wherever you want it to output. It'll output like a file, a folder full of files. That's the website. You run this, it'll build the website locally on your machine so you can test it and visualize everything that's going on. However, if this doesn't work because somehow you can't figure it out, which last year most people couldn't figure it out, which was mind-blowing. If you are at a pull request, so let's say like add student dates. When you've got your pull request, and it doesn't show it. If we go down here, let's see, this one isn't merged yet. You'll see all of these things here. These are the checks, right? So this text, like, did the unit test pass? Did the formatting pass and everything? Did you, like, basically, did you catastrophically break the website? This will tell me if you did. This will tell me if the website could build or not. If the website built, awesome. Okay? Now, if you can't figure out how to build your website locally, you go here, you click details, and it'll have all this stuff here. Why does it not show me the, maybe it won't. Well, on yours, if you go to the action, you'll see something that looks like this. Here, maybe actually I may have clicked it wrong. Let me just retest, see if I can figure this out correctly. It's because it's, whatever. If you go to your actions, you will see the action for all of the pull requests that were ever created. So you can go to yours, and if we scroll down, if we do, it creates an artifact. The artifact is the website build, because it builds the website to make sure it can build the website. And so it just kind of hangs out on GitHub. So you can download it. It'll be a compressed file. You unzip it, and then you can open it locally. Right? Let me show you, just in case. Okay. Raise your hand if you don't know what a zip file is. You can be honest. Okay, good. You extract it wherever you want. I'll just extract it here for testing purposes. It's taking a while. Must be a lot of small little files. And there we go. Then all you have to do just open the index. Index will be the whole web page, except this is not online, it's just saved locally. And you can navigate the website locally and you can go check your student lecture and whatnot. Your student lecture should be added under, by the way, I think I say it in the description, but if we go here to like, if you have this locally, you're gonna want it local in order to do the lecture. It'll be under Site, Student Lectures. That's where you put it, okay? Okay, cool. Any questions about this? Yeah.
Could you go back to where you said it was a stand-in? Like the little part on the GitHub?
Like the source, or like the
Yeah.
path variables? Yeah.
So that path, that's supposed to be a path to our own computer from where we're building it?
So let's say I am, I'll show you, right? No, I'm not in the virtual environment right now, so I won't be able to run it, but in here, let's say I was in like terminal. I would say like, I don't even think it'll know what Sphinx is because I'm not in the, yeah. Maybe? There. And then the source directory would be site, because I'm like in here. This is my working directory, right? So it would be in site, and I would put it in a new folder. Oh, build. Build doesn't exist. This would make build and then just dump everything in build. If I hit enter, it won't work because it'll be like, what the hell is this, right? Because I'm not in the virtual environment, but that's effectively what you would do. That's what I mean in terms of the directory. If you're opening up your terminal and you're in some other working directory, you're gonna need like full paths. Here, I don't need the full paths because I'm just in the working directory and I want the site. That's what I'm building. Cool? Cool, cool, cool. In fact, I'm curious if on GitHub, we can even see workflow Sphinx build. So like this is like an automated script that gets run on GitHub to create the virtual environment, install everything you need. Like you have Python, you install everything you need to get it working. You run the unit tests. I validate. That's a whole other thing. I run the unit tests. That's the testing, and then here's the other one, Sphinx. Install dependencies. Sphinx site. Sphinx build. I must have that actually already. I must have a script that exists, like I saved it as that. But nevertheless, that's where. Whatever. That's how it builds it on GitHub. Cool, 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 cool. Obviously, you're not going to completely understand this until you have a chance to sit down and sink your teeth into it, but I've given you a little bit of details. I believe I recorded all that. Good, I did record all that. Any last questions before we carry on with, yeah, I just want to make sure it's all described in on the lecture page, but I just want to make sure like it's, you've seen it. If you come back if you're making a lecture, I recommend you try to create your page. It could be empty. Like when you're like, how do I do this? Just look at any of the goddamn pages I already made and then just copy and paste what you need, right? I would recommend you you try to get it set up so like, okay, I've created it in the right folder. I can run these things locally. Try to do that for next class. And then if you have any questions, ask then. Ask earlier than later. And then if there's a trouble, maybe we can work through an example or something. Cool? Cool. All right. Now, yes?
Would it be something similar for the
Project presentation? It'll be like identical.
Identical.
Yeah. You would just, instead of under student lectures, I'd have you put it under like projects.
Okay.
Yeah. Cool? Cool, cool. Do I say, you know what? I don't know if I say in the, let me have a look here real quick. Yeah, okay, make it a web page. Yeah, okay, I do say that. Last chance for any questions or anything? We're happy, sad? Thumbs up? Okay. All right, presentation, no, okay. What comparing distributions mean. So we were talking about, look, we have two random variables, they could be whatever, and I want to say, if I didn't know any better, what is the likelihood that the observations I was making, like, a lot of times when you're doing this type of analysis, you're always trying to answer the question, how surprised should I be, right? So if I'm counting the number of people that walk by, well, let's do the drug trial example, okay? This is the drug trial example, okay? Let's say the dark gray box is, don't let me wander too far. This is charging, so if I wander too far, it won't pick up my voice very well. The drug trial. Typically this would be double blind, meaning let's say you're my patients. You don't know if you were given a placebo or the actual medicine. I don't know if you were given the placebo or medicine. I put it through the system, other people, maybe it's a program, I don't know, and it shuffles everybody, everyone gets a unique ID and it tells me just give this person this stuff, this person this stuff, this person this stuff. So I don't actually know. And this is a way to eliminate biases, okay? So it's a great way to eliminate bias where the data is the data. There will be a record later that we can go look up and be like, okay, who actually did and who did not get what? But that's the idea of double blind. So the point is, though, at the end of the day, one group of people was given a placebo and another group was given the special new drug. And this is the distribution of recovery times from the flu, and this is the distribution of recovery times of the flu. People who had the placebo, people who had the medicine, right? So the question I want to ask is, did it make a goddamn difference? Did it? Did this group get better results? If we go look at this right here, you might say, hey, the orange one is a little bit more this way, faster recovery time than the blue one. So that's a good thing. Clearly it worked. But did it really? That's the question we're asking. Okay? Is the question clear? Is it clear? Is it clear? Devin, is it clear? Yeah. Is it clear? It's clear. It's a clear question. Good. I need y'all to be engaged in this one because this is a big one. Today's lecture will change your life because you will actually understand what the hell it means when people compare things. You'll actually understand what the hell a p-value is. So did it make a difference? Meaning, imagine I deleted this data and I generated 50 data points and 50 data points again and plotted them. Would it look the same? Would it look different? There's a lot of data in here. Let's assume what we call, let's assume, if it made no difference, if the thing I'm trying to observe, if the new drug made no difference at all, it wouldn't matter what group. If the drug made no difference, it doesn't matter if this is orange or blue, right? It wouldn't actually matter, right? If it made no difference, I don't care who is in what group. That's what we call, does anyone know what we call this idea? I know you've heard it before, but again, you've had terrible teachers. This is what we call the null hypothesis. It makes no difference. If it makes no difference, We start with the assumption it makes no difference. And with this assumption, we actually get a lot of amazing power. Because if we assume that this makes no difference, then it should not have mattered if the person that was counted right here, that's one person, it looks like, based on the x-axis. This one person, according to what I collected, they didn't have the drug. But if it made no difference, they may have had the drug, it doesn't matter. Assuming it had no difference. Assuming it had no effect at all. All right, so with the above example, the average recovery time for the placebo group was 15.4 days. The drug group was 13.8 days. The drug group recovered, on average, 1.6 days faster. One may be very tempted to conclude that the drug clearly worked. However, the average recovery time is a summary statistic of a whole lot of information, a whole distribution. When observing a distribution, we can clearly see these two distributions have a lot more nuance to them than a single value. There's a lot more going on in these two distributions than 15.4 and 13.8. We also only had 50 observations. That's not a lot. We want as many as we can. And each individual is different, right? So there's noise in this data. There's going to be noise because every human is going to have a different reaction to every drug. It doesn't matter. Everyone's a little different. So if I were to do this again, if I were to repeat this whole process again, before doing any comparisons of distributions or anything, if I were to repeat this process again, what are the odds that this result would just happen by chance, where we had an average recovery time being exactly the same? If I were to recreate this experiment on a different group of people, the odds of getting these two exact same distributions is effectively zero. Like, that's not going to happen, right? Right? That's crazy to think. Maybe they'll be similar, maybe they won't be. I don't know. So if I were to do this again, what are the odds that this result just happened by chance? Like, we all agree it's entirely possible that, look, I took 50 observations. I know you've all hit run on your GA several times and you get a little bit different results every time, right? In fact, the results might be wildly different every time you hit run, right? It can happen. So this instance, I had 15.4 and 13.8. If I run it again, are they going to be the same? Are they going to be different? How different? If I do this all again, what's the odds that this is going to happen? I'm going to get like similar results. So the null hypothesis. Always start by assuming that there's no real difference. This drug has no effect. And this is, like I said, this is a very important assumption. It may feel like an arbitrary position to take. One might say, why don't you start by assuming that they are different? Then you can just do. It does seem like an arbitrary position to take, but with this assumption, it allows us to start to form a very important argument. Now, I hope you've been paying attention up until this point, but now's the point where you really need to be paying attention. Nothing I'm about to say requires any significant logical leap. You are all 100% capable of following my train of thought here. Assume the drug has no effect on recovery time. Okay? Okay. So let's start by we could take it further from an assumption. Let's pretend I'm here standing. This drug has no effect. Those distributions you saw, the fact that they were different, pure dumb luck of the lottery, of rolling the dice, pure dumb luck. These drugs have no impact at all. What we saw was dumb luck. That's it. Okay? If this is the case, if the drug had no impact, then it could be expected that the average recovery time would be no different than the placebo, right? If the drug has no effect, the average recovery time should be effectively the same. We saw that they were a little bit different, but again, that was just by rolling the dice. So if the drug has no impact, we should expect the recovery time to be the same. If both groups had a placebo, it wouldn't matter which person was assigned to which group. Okay? If the drug had no impact, it wouldn't matter if I gave you the drug or the placebo in the final result. It wouldn't matter if I gave you the drug or the placebo. It wouldn't matter if I gave you the drug or the placebo, and so on and so on and so on. It wouldn't matter because, again, this drug had no impact. It had no effect. It's like I'm giving you a placebo either way. It wouldn't matter which one I gave you. So far, so good? I hope so. Then it should be possible, if the drug had no impact, it should be possible to assign each individual and their corresponding recovery time. So each of you was in my drug trial, and you have a recovery time of 11 days. You have 15 days. You have 19 days. You have, and so on and so on, whatever. You all have your recovery times, right? And you all, you had a placebo, maybe you didn't, but that part doesn't matter. You all know your recovery times. So it should be possible to kind of go back in time and pretend that we can assign each individual and their corresponding recovery time to one of the two groups randomly, right? So if it made no difference, let's pretend, even though I gave you the drug, I can pretend I didn't give you the drug because it has no difference. Same with you, I can flip it. I can flip it, I can flip it. It doesn't matter. It should not matter if you had the placebo or not. That had no effect on your recovery time. Okay? The difference in the average recovery time between the two randomly assigned groups would be an example of what one would expect with dumb luck. Okay? So let's say I take everybody. There was 100 people in this example, right? 50 in one group, 50 in the other. Let's say I shuffle them and say whether or not they actually had the placebo or the drug, we put them into the drug group, and we put them into the placebo group. If it had no impact, and we do that, and we take, well, what's this group's average recovery time, and what's this group's average recovery time, right? This is like the bastardized groups, right? Some of them really had the placebo and some of them didn't, but we're assuming it makes no difference. So, if it makes no difference, the average recovery time from here and the average recovery time from here, I can look at that and look at the difference in the average recovery time. It's actually important to pay attention that we're actually looking at the difference in the average recovery times. Not what is their average recovery time, what is their average recovery time. Remember how I said there was a difference of 1.6 days or whatever? Well, let's randomly assign people to groups and take their average, take their average, and what's their difference? Was it 1.6 days? Was it negative 1.6 days? Was it 4 days? Was it 0.1 day? The difference, it should be arbitrary. If it makes no difference, it doesn't matter what group they were in. I can pretend they got the drug and didn't get the drug, take the average recovery time of the drug group, take the average recovery time of the placebo group, and see, well, what was the difference? Right? That would be an example of, that would be because obviously if I take a group of 100 people and I shuffle them, and I do it again, the groups are going to be different, right? So I can keep doing this and get a different group and a different group. Is that clear? Those would be examples of, if it made no difference, then it doesn't matter. That would be an example of the dumb luck difference. Right? Are you sure you understand this? I really hope you're not just nodding and smiling. This is important for you to understand. Do we have any questions, thoughts, concerns, comments at all? Now is the time to ask. Yes?
I was just thinking, could you theoretically, if you knew the drug maybe did something, could you do two groups of placebo and one group with the drug, and then compare the groups of placebo to each other, and then compare a placebo to the drug to see if there's a difference, to see if there's a larger difference between the two placebos?
You could do whatever you want. But hang on that thought, because I think you might see what, like, where we're going. Kind of, I'm guessing answers the same, like, addresses exactly what you're thinking. If it didn't matter and I randomly assigned 50 people to one group and 50 people to another group, their distributions, maybe their distributions look exactly like this, right? I'm saying, this is based on my null hypothesis, I am saying this is an example of a dumb luck distribution. I took 50 people, there's the distribution, took another 50 people, here's the distribution. And by dumb luck, that's the recovery times of the two groups. The average recovery times are this. That was just dumb luck. That had, the actual drug had no effect. Cool? Cool. And if that's the case, it should not have mattered if I gave you a placebo or not. We can pretend everyone had a placebo. Let's take 50 of the placebo group and put them over there and put the other one there. What's their average recovery time difference? Do it again. 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 This is where we get to the permutation or randomization test. Permutation sometimes is computationally intractable, meaning you ain't going to do it. Randomization is our way to kind of deal with that, which you'll see very shortly makes perfect sense. So assuming the null hypothesis, shuffling the group once and calculating the difference between the group averages will give one example of a chance difference. It's possible for me to generate every single combination of assigning the 100 people to two groups. Right? We can do that. If all possible combinations are generated, all possible average by chance differences can be calculated. Right? We're assuming it makes no difference. Now, in this example, there's a lot. There's actually times 10 to the 29 combinations of splitting 100 people into two groups of 50. So in cases where it is intractable to generate, what you do is you just repeat, instead of taking every single possible combination, you just shuffle it like a million times and go like, okay, that's probably going to be enough. We've taken a million samples of randomly assigning groups. So here are literally a million combinations and their average differences. This is not a distribution of recovery times. What I did is I generated a million randomly split groups, 50-50 of the 100 people. Okay? I calculated that group for every million, for every time of the million, I calculated the drug group's average recovery time and the placebo group's average recovery time and calculated their difference and plotted it here. And I did that a million times. And this is the average group difference plotted. Okay? So, when you look at that, it really looks like the majority of the time, the average recovery time of the two was close to zero. The average difference in recovery time was close to zero. Meaning, the drug really, I look at this and immediately go like, oh, okay, so, and this makes perfect sense. The drug makes no difference. So let's randomly assign each person to a group, and what was their total recovery time, whether they had the drug or not. We assume in that group, every person had the drug or not, right? What was their average recovery time? You're going to get something that looks like this in the end, hovering around zero. Yeah? Cool. But what's interesting is the shape of this distribution. Okay. So how do I interpret this? Like, what does this all mean, right? Well, the key question to ask now is, well, hold on. I did all of this assuming the drug made no difference, meaning it wouldn't matter if someone had a drug or not. I could arbitrarily assign them to one of two groups, and I want to see what is the dumb luck chance of arbitrarily assigning a person to a group and their corresponding recovery time to one of two groups just by chance. Like that's what's the key thing is we're starting with the null hypothesis. Yeah? The key question to ask is, how likely is it that my original observation, this is where we now kind of like hit pause on our null hypothesis and we say like, okay, this is a distribution of 1,000,000 dumb luck chance difference in the two groups. But my original observation was the difference was minus 1.6 days. Right? So this is the dumb luck distribution. If it makes no difference, this is the distribution of the differences I expect to see. There's 1,000,000 data points here. Okay? But I actually saw, like this is my actual observation in my group. My group, which could have been dumb luck, it could have been. But this is what I observed. So, out of 1,000,000, how many combinations would there have been that have a difference of minus 1.6 days or better? What are the odds that what I observed happened by chance? Very small. Of 1,000,000, I don't know, how many are there? I probably have it written down. There are 1,000,000. There were 205 observations that had a recovery time with the same or better. So if this is the by chance, I have a 205 out of 1,000,000 chance that this happened by dumb luck, or a 0.0205% chance. That's very little. All right? There's roughly a 1 in 50,000 chance that this happened by dumb luck. That's the p-value. That's what a p-value is. When you do a t-test and get a p-value, a t-test is a quick and dirty way to try to give you this information. But really what we want to do is a permutation test. It's just if you have a pencil and a paper and I say, go randomly assign this 100 people to two groups of 50 1,000,000 times, you're going to say, no, I'm not going to do that. But with a computer, it's trivial. So this is imagine I actually did every single possible combination. I generated every single possible combination, all times 10 to the 29, right? Assuming our 1,000,000 was a good sample of that times 10 to the 29, we would have a distribution that looks effectively like this. That is every single possible combination. It could have happened, right? It could have happened. I'm rolling the dice, it could happen. But we're certainly way more likely by chance to have a difference in recovery time of 0, but I didn't see a difference of recovery time of 0. I saw it over here. And very few of the by chance observations happened at that time or better. So what's the probability that what I observed was by chance? Well, how many of the total observations are here or better? And depending on which way you're going, you might be over here and being like here or better. But the p-value is literally, what is the chance of this happening by chance? That's what the p-value is telling you. So, okay, this is what a p-value is. There's a 0.000205 probability that the drug's improved recovery time actually happened by chance. So assuming the null hypothesis, what are the odds that what I saw happened by chance? Very little. Very few of the by chance differences was that good. It is possible, but if we were to be in a world where we're rolling the dice, it's a 1 in 50,000 chance that it's going to happen by chance. Very slim. It's possible. Now, when you look at modern research and everyone talks about a p-value of 5%, that's a 1 in 20 chance that your result was bullshit, by the way. Let that sink in, okay? There's two things you need to understand about modern research. Is this line is way further this way. They're only looking for a 1 in 20 chance. If it's a 1 in 20 chance that something happened by chance, they're like, therefore, it must be significant. 1 in 20. That's insane. That's why whenever you're writing any scientific paper, and this gets, I'm not going to name them, but there are some fields of research that are really bad where they don't even tell you the p-values. They'll just say it was significant or not. They don't even tell you. They'll be like, it was less than 0.05. Yeah.
Wouldn't they have to repeat the study so many times, though, and would that drop your p-value?
Well, they do it 1 in 20. 1 in 20. You can repeat the process. Well, if you repeat the hold on. Actually, it's unclear. Like, do you mean like a reproduction study? Reproduction studies are really a problem because no one wants to fund reproduction studies. I don't get money to recreate someone's experiment, so I can't actually validate someone's results. I just kind of have to take their word for it, which is also really bad. And in a world where it's a 1 in 20 chance, basically you could take 20 papers where the results are significant, and 1 in 20 of them is certainly bullshit. And it's not even necessarily their fault. It's just, it's bullshit. Like that, if 0.05 is what we care about. That's why when you're doing anything, always report the p-value. It's way more interesting. And sometimes the p-value, we get stuck, especially when you're young and you're learning all this stuff, you get stuck to focus so much on 0.05. What does the p-value tell you? Sometimes a big p-value is meaningful. I want to show things are the same. If I really want to show you that something makes no difference and I get a p-value of 0.05, uh-oh, they certainly are different, it seems like. There's a very small chance they're the same. So the p-value, it all depends on what are we trying to say. What are we trying to show? When I tell you a p-value of 0.0205%, yeah, that's a small, like that's so meaningful. Okay? So just be aware what a p-value really means. 1 in 20 is wrong. And that's not even getting into p-hacking. Do you know what p-hacking is?
Falsifying your results?
Well, yes, but like, it's a 1 in 20 chance, and I hit run, and I get a p-value of 0.1. It's a 1 in 20 chance. Let's hit run again. Let's hit run again. Let's hit run again. Let's hit run. Oh, there it is. It's so easy to cheese. And if you go, people have done meta-analyses. This is not a joke. Do you not know this? Do you not know this? This is crazy. This is crazy. This is how much like modern science is bullshit. And I'm not blaming the scientists. I kind of am. But you have to understand that it's all based on one of the incentives. And the incentives are there to cheat because effectively they've gamified modern research. And that's always a problem whenever you gamify something because then people game the game, not the actual thing. It's like whenever you have a metric, like a call center has a metric for like throughput, right? They want to maximize throughput, and someone who's really good at their job might have a really bad throughput, right? But they can solve the problems. But the companies only care about throughput, so the smart employees game the metric by just getting people off the phone. It's the same thing with research. Like, what are the incentives? They're incentivized to get things. Anyways, if you do a meta-analysis and you take a histogram of the p-values observed, and you look at like the p-values, and you're like, okay, here's like 0.1, 0.5, 0.05, 0.01, right? And this is the 0.5. If you go and you look at the literature and you do a meta-analysis and go look at all the articles and look at what the reported p-value is, this is what you see. Meaning, if I want to show something is significantly different or not significantly different, meaning you should assume something like this, right? You should assume your average likelihood of getting a p-value is kind of like whatever. Isn't it weird that everyone's p-value is just past the significant threshold? Which, when you ask, who decided 5% in the first place? No one goddamn knows. Someone said, 5%? Okay, let's go with that. There we go, right? Like, it's nonsense. So all of the researchers are effectively lying. How is it that, like, the majority of things reported are right around 0.05? See if we can, let me see if I can find, like, the actual plot. Alpha... Cheating, p hacking. No, it's not going to be. Of course, I can't find.
That P curve one was pretty interesting.
This one here is kind of showing you. It's kind of showing the same idea. It's not quite the one I had in mind, but you can see, like, this is what you would expect. This nice curve. But then why is there so many why is there a little like, and so few on that, like, that's weird. It's because they're cheating. Yeah. Whoop.
We'll always have to optimize for something.
Pardon?
We'll always have to optimize for something.
Yep. So anyways, that's the p-value. This is the dumb luck distribution of differences. It didn't matter which group they were from. I just randomly assigned, because if it didn't matter, it didn't matter. It's like I took a group of 100 people that took neither drug. They didn't have the placebo or the medicine. And I split them, like, that's what the assumption is. If it makes no difference, it would be like doing that. But this is what I observed. This is what I actually observed. And what are the odds of what I actually observed? What were the odds of all the possible dumb luck configurations? Because remember, there is, like, it's impossible to get a p-value of 0 because at least one combination of people got 50 people got the drug, 50 people got the placebo, right? That is a possible dumb luck configuration, right? That is at least one of the times 10 to the 29. Right? So there's always at least a p-value of 1 over however many combinations of the things there are. There's always a chance that, well, it could have happened that the people you picked just kind of were worked out that way. So there's never a 0 p-value. Some people will ignore that one. They shouldn't. They really shouldn't. You should always count that one. Now, what does this mean for you? Now, look. Realistically, whenever you're doing an analysis, what you should be doing is the permutation test. You should be doing this. Or a randomization test if the permutation test is not realistic. The permutation test, I just showed you one use of the permutation test. The permutation test can show you whatever the hell you want. It can measure any statistic. You can measure the differences in the means. You can measure the differences in anything the hell you want. Okay? There are Python libraries that are like scipy.stats, I'm pretty sure allows you to do a permutation test. You just have to read the documentation and maybe find like a YouTube video of how someone used it, because it's there's a little bit more nuance to using the permutation test than something like a t-test or a Mann-Whitney-U test. But really what you want to do is a permutation test, okay? If you can't wrap your head around it, which you all should be able to, but I get it, you know, only so many hours in the day. If you can't wrap your head around it, you can use something like a t-test. A t-test is like a quick and dirty way to approximate these results. Arguably, if you had to pick between, there's another thing called the Mann-Whitney-U test. How many of you have heard of that one before? How many of you have heard of a t-test before, though? Yeah, that's weird because this is by far the better one of the two to do. And it's in computer scientists tend to like this one more because it's very algorithmic. It's a non-parametric, meaning it requires, like, we don't need to assume some parameter. We can make fewer assumptions. That's long story short. So do this one. The good news is you could say like scipy.stats.manwhitneyu, open parenthesis, list of results, comma, list of results, enter. Boom, you'll get your p-value back. It's easy to use. In the same way that the t-test is too. But if you wanted to do one of the quick and dirty ones, this is, I would say, the better one of the two to use. Do you have any questions? Now, what I would like you to do is really think about this topic, because I get that, sure you learned something, but like how much did you really grasp it? I want to make sure you actually really understand this, because this is going to be critical. Like, what does this really mean? Decoding a lot of what people say and understanding what you can do to show what you need to show. And then if you have questions, ask them next time and maybe we can figure it out. Anything before we leave? All right, I'll see y'all later.